everyone here for your attendance today. This webinar will be recorded and made available at Ozen Engineering website, which is www.ozeninc.com. So if you miss some part of it, you will have a chance to capture from that saved recording. So today we are starting a 5-week-long webinar series on fracture mechanics and fatigue crack propagation in ANSYS release 16. And if you would like to see the full schedule and register for the next events, you can go to the Ozen Engineering website, and it's at the front page right now. Just look for the fracture mechanics in ANSYS R16 webinar series. So today we will start with an introduction to fracture mechanics and understand why it is important for structural designers. Of course, we will look briefly at what ANSYS offers in fracture mechanics fields as well. Some of the material presented today, as Metin have mentioned, includes new enhancements in the ANSYS mechanical software like the XFAM method, the Seastar Integral, and the material force support for hyperelastic materials. This week's presentation will be the most theoretical one and will not include a live demonstration of the ANSYS mechanical software. Here we wanted to provide an overall picture of why we do fracture analysis and what is available first. Following series will have a dedicated demonstration of the software in action. So I just wanted to go over these items very briefly. So let's get started with our webinar here. So one important thing is actually before doing any fatigue or fracture mechanics calculation, it is a must to decide on a design philosophy. Will the component at hand be regularly inspected and taken out of the service when cracks are found, like in aerospace industry, or is it to be taken out of service before there is even any possibility of cracks forming, like in mission critical designs? Answering such questions will guide the analyst to decide on a design philosophy. And there are really mainly 3 different approaches, which can be as listed as safe life, fail-safe, and damage tolerant. And these images for a different type of swing designs, they really represent these different approaches here. In the safe life philosophy, products are designed to survive a specific design life and with a chosen safety buffer. The estimated life can either be calculated or obtained via testing. Then the design life is set as a fraction of this estimated life. It is really common to use 1/5 of the calculated design life for safety critical components. Whereas in fail-safe philosophy, the product is designed such that specific type of failure results in no harm to other structures or personnel. With regular maintenance, the failed components can be replaced without much affecting the overall product performance. Damage-tolerant philosophy, which is the last item here, can be seen as a compromise between the safe life and fail-safe design approaches. With this approach, the product is designed with some built-in redundancy such that it meets fail-safe parts, and also it is regularly inspected for cracks such that cracked components can be serviced in time. With this approach, it is important to have information about the loading, how that loading affects crack growth, and how big a crack results in immediate collapse. This is really the discipline of fracture mechanics as we have described, which we will be covering today and on the following 4 weeks within its applications in ANSYS software. So what is fracture mechanics? That's an important question. Fracture mechanics is the field of mechanics concerned with the study of propagation of cracks in materials. This is like a dictionary definition of it. It uses methods of analytical solid mechanics to calculate the driving force on a crack and those of experimental solid mechanics to characterize the material's resistance to fracture. Fracture mechanics can be seen as a special case among different philosophies. Safe life design normally uses stress life analysis, and the usual damage-tolerant design philosophy uses crack propagation, i.e. fracture mechanics, to estimate life. We will see at week number 5 of this webinar series about fatigue crack propagation, and Metin will be presenting that webinar. There we'll be talking about stress life and strain life methods for fatigue crack propagation. So talking about the strength of material approach, it relies on the calculation of stress on components based on the load they are experiencing. Generally, material flows are not considered, or if known, a specific stress concentration factor is simply applied. However, this approach doesn't provide valuable information about the failure due to fracture cracking. And it is known that in presence of a crack, as seen here, the crack tip stress levels can increase considerably high and result in failure even if the overall stress levels in this component is considerably low from a strength of material perspective. So what does fracture mechanics bring in here? The answer is fracture mechanics really presents new parameters to assess failure. Flow size, which is usually denoted with a letter A, is an important parameter. The critical limit for failure is determined via the parameter called fracture toughness, which replaces the strength of material. As we will see in more detail, the material behavior is a key parameter to pick the correct methodology in performing fracture mechanics analysis. For linear elastic fracture mechanics, fracture toughness of a material is determined from the stress intensity factor. The elastic plastic fracture mechanics, fracture toughness is determined via energy required to grow a crack, and the J integral is the parameter that can be used for that calculation. So once again, we will be talking more on parameters like stress intensity factor and the J integral. At this point, this is only important that fracture mechanics calculations provide new set of parameters for calculating and assessing fracture failure, and these depend on material behavior, whether we are working linear elasticity, plasticity, creep, or any other behavior. So fracture mechanics discipline spans a broad range of industries. One can probably argue that any industry dealing with structures and/or using the damage-tolerant design philosophy will apply fracture mechanics in their design. A few to name is automotive, electronics, healthcare, aviation, civil engineering, and nuclear, and I assume there is for sure a field I missed to list here, but I'm again sorry for that. So we talked about the different design approaches, 3 of them actually, for structural calculations, and briefly mentioned the strength of material and fracture mechanics as 2 alternative or better complementary methods. It is important to note that historical background which yielded the fracture mechanics field to develop. So here we will be talking about some history, and as we will see, there are numerous critical accidents from different industries which laid out rules for design for fracture failure. And the first example is the Comet airplane crash. It is one of the most important instances where cracking resulted total loss of airplanes and lives. The Comet was the first production commercial jet airliner that went into service in 1952, about 60 years ago. And within 2 years of entering service in 1954, 2 of the Comet fleet fell apart during ascending to cruise altitude. Investigations after the incidents included pressurization tests of the fuselage in a water tank and fatigue cycling, and the evidence of fatigue cracking was found on the corners of the escape hatch and side windows. There were lessons learned from these accidents. Weaving windows are no longer designed square, but with round edges to reduce any stress concentration. And also, crack stoppers are now placed between frame cutouts by breaking the fuselage into multiple sections. And this way, propagation of one crack from one section to another is prevented, which would otherwise result in large and more catastrophic failures. And another example is from defense or maritime industry, if we call it. As part of the government project during World War II, United States planned continuous block construction of all welded cargo vessels, which are called the Liberty ships, as you see here in this picture. During World War II, there were above 1,000 instances of significant brittle fractures in these ships, and 12 ships, including 3 of the number of total Liberty ships built, by the way, is 2,710. Including 3 of these ships, they really broke in half without any warning, and about 200 of them sink or damage beyond all hope of repair. So that's an important number here. And one of the factors in failure of Liberty ships were them being built with block welding, predominantly welded, as opposed to riveted hull construction allowed cracks to run for large distances unimpeded. So this is one of the design rules actually we have seen just a couple slides ago, by separating the fuselage into multiple sections. Just the quite opposite design was taken here, and it resulted in these catastrophic failures. A Cambridge University study revealed that ships in North Atlantic were exposed to temperatures that could fall below a critical point when the mechanism of failure changed from ductile to brittle. As we see on the lower left hand side here, the fracture toughness, the critical stress intensity factor, it is a function of temperature really. So of course there were more accidents. Another accident from aviation industry is the Aloha Flight number 243. The Aloha Flight accident occurred on 1988. In this case, the plane was a Boeing 737 and suffered extensive damage after an explosive decompression in flight. There was one flight attendant died, and luckily, the plane was able to land safely to Maui. The failure mechanism was reported as a result of multiple side fatigue cracking of the skin adjacent to rivet holes along the lap joint, and tear strap disbond, which negated the fail-safe characteristics of the fuselage. Another incident was a train accident, actually happened in Germany. The Eschede train disaster occurred in actually 10 years after the Aloha Flight incident in 1998, when a high-speed train derailed and crashed into a road bridge. In this instance, 101 people died and around another 100 were injured. It remains the worst high-speed rail disaster worldwide. And the cause here was a single fatigue crack in one of the wheels, which, when it finally failed, caused the train to derail at a switch. So for some components, the crack propagation life is neglected in the design because stress levels are high and or the critical flow size is small. For other components, the crack growth life might be a substantial portion of the total life of the assembly. Moreover, pre-existing flaws or sharp design features may significantly reduce or nearly eliminate the crack initiation portion of the fatigue life of a component. The useful life of these components may be governed by the rate of subcritical crack propagation, which is the second region here as we see it. The rate of fatigue crack propagation is determined by subjecting fatigue crack specimens, like the contact specimen used in fracture toughness testing, to constant amplitude cyclic load. And the output from such tests is really these type of graphs where the x-axis shows the number of cycles and the y-axis shows the flow size, which is also known as the crack length. This type of data can be done by varying the magnitude of cyclic loading or the crack size, and the data can be reduced to a single curve by presenting the data in terms of a crack growth rate per cyclic of loading, which is dA by dN, as we see here on the right hand side, versus the fluctuation of the stress intensity factor at the tip of the crack, which is designated by delta K. Delta K is representative of the mechanical driving force, and it incorporates the effect of changing crack length and the magnitude of the cyclic loading. So it is generally accepted that in general fatigue cracks start following the nucleation of a crack on a persistent slip band, which is really part of this initiation stage. As we see here in this graph, it's again this A versus N graph. After crack initiation, there are two stages of stable crack propagation before a third unstable growth causes failure. The initial stage is concerned with the propagation of small cracks over a few grain boundaries and takes up little of the lifespan. And the stable region, where the crack speed grows exponentially with the crack size, is really the simulation context that we are looking at when we talk about performing fracture mechanics analysis using ANSYS mechanical tool. As we have mentioned before, crack initiation takes up little of the overall lifespan, and still it's an area of concern for determining structural reliability. It is known that cracks initiate from an imperfection, an already existing crack, and a locally weakened area. And in such cases, a failure analysis must include the fracture mechanics analysis. A strand life is one working method that we have at the present for predicting the so-called life to crack initiation. So looking at the past of the development of the fracture mechanics discipline, Griffith, who was born in the century before, was an English engineer who, among many other contributions, is best known for his work on stress and fracture in metals that is now known as metal fatigue. Griffith published the results of his theoretical calculations and experiments on brittle fracture using glass material in 1920, and he found that the strength of glass depended on the size of microscopic cracks, and the equation is stated here. So if S is the nominal stress and A is the crack size of the fracture, Griffith showed that the following relation holds as we see here. And this is the graph. Griffith has Griffith's actual theory is put on the image here, shows the relation where the stress times the square root of the flow size is constant, as we see here. There are three ways of applying a force to enable a crack to propagate, and these are also called the different modes of fracture. So if you go over all of them, the mode 1 denotes a symmetric opening, as we see here, the relative displacements between corresponding pairs being normal to the fracture surface, and it's also called the opening or the tension mode. Mode 2 denotes an anti-symmetric separation. The relative displacements or the relative tangential displacements between corresponding pairs being normal to the crack front. It's also called the in-plane shear mode. And mode 3 denotes an anti-symmetric separation again, but this time the relative tangential displacement between the corresponding pairs being parallel to the crack front. It is also called the out-of-plane shear or tearing mode. In general, crack growth is a function of any of these modes or a combination of 2 or 3 modes. However, crack growth usually takes place in mode 1, or to close it, the crack basically adjusts itself such that the load is perpendicular to the crack faces. Typical fracture mechanic parameters describe either the energy release rate or the amplitude of the stress and deformation fields ahead of the crack tip, and here we have listed these parameters. The parameters that are widely used in fracture mechanics analysis can be listed here, starting with the J integral and then the energy release rate, stress intensity factor, T stress, and material force. I have listed here the UMM method, which is the unstructured mesh method, which is not actually a method for fracture mechanics but or finite element analysis to make use of unstructured mesh available for fracture mechanics parameter calculations. Otherwise, it's known that the above methods strictly requires structured mesh to calculate those fracture mechanics parameters. So if we would like to go through all these parameters very briefly, first, the energy release rate, it can be calculated from stress intensity factors and also using the J integral. The J integral can be defined as a path-independent line integral that measures the strength of the singular stresses and strains near a crack tip. J integral can be calculated using ANSYS, and the details actually we will be going through in the next series, and it can be also found in ANSYS help documentation. Using J integral, materials other than linear isotropic like orthotropic, functional graded, or elastic plastic materials can be studied for cracks. So when the load and crack size are kept below the threshold point of unstable crack extension, which is the region number 2 if you remember from the earlier slides, the magnitude of stress felt in the immediate vicinity of the crack tip is measured by the so-called the stress intensity factor, and it is associated with the stresses. The stress intensity factor is a quantity determined analytically and varies as a function of the crack configuration and the manner in which the external loads are applied. However, the critical stress intensity factor is independent of the crack geometry and loading and may be regarded as a material constant. So here we see typical critical stress intensity factor values for aluminum and steel. So in strength of material approach, one would look at the ultimate strength value, and here in the fracture mechanics approach, those values are replaced with the critical stress intensity factor or the so-called fracture toughness values. Another important fracture parameter is called the T-stress. It is the stress acting parallel to the crack faces and is linked to the level of crack tip triaxiality. In other words, it provides three-dimensional information about the crack. Unlike J integral, it can have both positive and negative values, and its sign and magnitude provides valuable information about the size and shape of the crack tip plastic zone. And negative T-stress values decrease the level of crack tip triaxiality, i.e. leading to larger plastic zones, while positive values increase the level of triaxiality, i.e. leading to smaller plastic zones. A higher crack tip triaxiality promotes fracture because the input of external work is dissipated less by the global plastic deformation and is thus available to augment local material degradation and damage. Material force method material force is another parameter of fracture mechanics. This method provides parameters for determining near-tip crack driving forces. It is based on continuum mechanics and material force vectors that act on imperfections, discontinuities, and dislocations. As an example, the material force can be imagined as a force opening zipper in a pre-cracked structure as shown in this slide. If the crack driving force gets large enough to reach the critical value or the fracture toughness of the material, fracture occurs and the crack propagates in the direction of the inverse of the crack driving force, which is seen here at the sharp crack tip. The method can be applied to all kinds of material models, either linear or nonlinear, time-dependent, temperature or moisture effects can be taken into account, as well as viscoelasticity, anisotropy, and etc. So as you can see, this is one of the most comprehensive methods in terms of the material models in ANSYS currently. Interested attendants can refer to one white paper from ANSYS, which is titled Material Forces, a Novel Approach to Fracture Mechanics in ANSYS. So this paper, which I read as well, it provides a detailed explanation of the material force approach. So going to another parameter, here we see the Seastar Integral, and here Seastar Integral is used to evaluate the crack tip fields in a homogeneous material undergoing a steady state creeping deformation. Crack growth has been relatively recently considered as a branch of fracture mechanics over the past 40 years, and it generally becomes a concern when structural components are operated at high temperatures. And as an example, you can think of the nuclear power plants industry, where parts are operating at high temperatures. This is one parameter in fracture mechanics that helps in assessing materials at high temperature for fracture mechanics. And Seastar Integral is a path-independent integral like the J integral, which is the steady-state creep analog of J integral and could be useful as a creep fracture parameter. Okay. So we have already mentioned that the unstructured mesh method is not a parameter, but it's a method. It is a numerical tool used for evaluating fracture mechanics parameters more accurately in cases where unstructural hexahedral meshes and tetrahedral meshes are used. The accuracy of the resulting parameters is generally comparable to that of parameters evaluated using structural hexahedral meshes. So one might ask, why is there this many different methods or parameters to calculate fracture mechanics? And the answer to that question is that each method provides solutions under different set of material behavior. When calculating energy release rates with the VCCT method, the mesh in the vicinity of the crack must contain only 2D or quad elements or 3D hex elements. That's one limitation. And also in terms of material behavior, one has to use linear isotropic, orthotropic, and isotropic elasticity only. But with J integral, for example, designers can analyze for both elasticity and plasticity cases. So ANSYS provides alternative methods to simulate the crack growth as well in homogeneous and composite structures. Cracks may propagate when certain loading conditions are reached or certain localized conditions are met, or can propagate along the interface between the layers of a composite structure, i.e. the interfacial delamination. And depending on the case, one can simulate crack growth along a predefined path or along an arbitrary path. The VCCT-based crack growth simulation and cohesive zone modeling can be used for crack growth along interfaces, that is the predefined interfaces. And the XFAM-based crack growth simulation technique simulates crack growth along an arbitrary path and strictly in linear elastic homogeneous materials. And we will have actually two webinars, specifically one on XFAM method and one on cohesive zone and VCCT based interface element method crack propagation techniques. Considering the fracture mechanics using finite element analysis, the crack tip meshing needs special attention if one doesn't use the unstructured mesh method. And the kscon command is one critical command in ANSYS mechanical APDL, which is used to generate elements around the crack tip with skewed mid-side nodes as seen in here. The mid-side nodes ideally should be close to crack tip at 1/4 of the element edge length, and this way the crack tip 1/√R singularity can be captured. In terms of element types and support by ANSYS for fracture mechanics, ANSYS supports fracture mechanics calculations on certain structural element types as listed in this table, and this table can be found actually in the ANSYS APDL fracture analysis guide. And this guide is actually, there wasn't such a guide with the previous version, but it's a new guide which you can find either as a PDF version or in ANSYS help of release number 16. And most fracture calculations rely on the element nodal connectivity order and must conform to the pattern specific to each element. CINT and KCalc commands are the two important commands to define fracture mechanics parameter calculations. Towards the end of our webinar, we will briefly show some simpler applications, starting with this case which shows one of the well-known introduction problems to fracture mechanics, i.e. the 2D edge crack propagation problem. It can be solved for plane stress and plane strain, where these two approaches can be employed to observe and verify with analytical solutions with FEA results. And this problem can be solved using both fracture mechanic tools and cohesive zone elements in ANSYS. So here we see an animation of the case where we make the crack propagate starting from the edge. In this application, we have used ANSYS mechanical APDL to calculate fracture parameters, that is the stress intensity factors for mode 1 and mode 2, to determine crack propagation and its direction. In order to capture the crack tip singularity, kscon command for crack tip meshing was used. Stress intensity factors are calculated by means of KCalc or CINT command directly. The crack initiation angle and the energy release rate can be calculated with analytical relations using stress intensity factors, as we have seen in the definition of the energy release rate. So there was one specific slide if you recall. And the cracks are propagated in the maximum tangential stress direction, i.e. that is the parallel direction to the loading direction, to attain pure mode 1 opening conditions. So another example is the thin film cracking. It is an interesting field, especially in the electronics industry, and has various applications. And this application here that I'm going to show was actually part of my thesis work, where I have studied the crack propagation in a silicon oxide thin film on a silicon substrate. The crack front and the crack-to-crack interactions and the interactions of cracks with free surfaces, as in here, were analyzed with effects of interface modeling using cohesive zone elements. So this model included several aspects we have talked over this presentation today actually. So here we see another animation. The animation on the left hand side is showing the crack propagation in this silicon oxide thin film under thermal strain loading conditions. Here in this case, ANSYS mechanical APDL was used to perform these analyses where the crack propagation is handled within a global loop. Each propagation step is handled under quasi-static assumption, where fracture parameters are calculated at each propagation step and the geometry and mesh is updated for the next propagation step consecutively. Cohesive zone elements are placed in between the film and the substrate to model interface delamination. The graph on the right hand side shows the crack propagation path as crack front turns toward the 45-degree free surface cut. So this is showing how the crack interacts with the free surfaces next to its front. An industrial example here is performed on the infamous pump housing, which you may have seen in ANSYS workbench introduction demonstrations. With an ANSYS workbench you can define cracks and incorporate crack mesh directly into finite element mesh without modifying the geometry. And again, next week actually we will be having the fracture mechanics in ANSYS workbench webinar, and here Metin will show how you can achieve that. And in addition to stress and deformation results, as we see here on the lower left hand corner, one can obtain the stress intensity factors and the J integral values as shown here on the lower right hand corner. It is important to note that ANSYS provides support for not only structural loads but also for thermal strains and crack face pressure loads. So that's one of the important aspects. So here's another example, another industrial example. It's a cracked helicopter flange plate, and this example actually has a short history. In early 2000, in 2002 specifically, this American helicopter industry initiated and opened a challenge to finite element analysis vendors to analyze cracking on a helicopter dynamic part. In this case, as you've seen on the upper left-hand corner, a rectangular flanged plate. And this part geometry and the loading history was considered to be complicated. We here in this slide we don't show you the loading history, but it's an irregular time versus loading history graph that was supplied to the vendors. And here the aim of the challenge was to benchmark different fatigue crack growth simulation methods. An ANSYS solution to this problem was to use ANSYS workbench framework with a Python scripting capability, as it will provide minimal user intervention setup. And here, as you may have noticed, the fracture mechanics part is solved on a submodel, which is shown here as a part of the more coarse meshed global model. And we are going to see how one can perform such analysis again in workbench more in detail in the following week, where Metin will be presenting fracture mechanic analysis in workbench. So with this, we really finished our material to present for today. And before saying goodbye, I would like to remind you our scheduled webinar series for the following months. And there will be 4 different webinars on fracture mechanics in ANSYS R16. So next week we will be talking about fracture mechanics analysis in Workbench for those who are interested in seeing the software in action. This will be the time, so there will be a live demonstration. And Metin Ozen, founder of Ozen Engineering, will be giving this webinar. And following weeks, we will be talking about the XFAM meshless method, which is recently added to ANSYS R16, and cohesive zone and delamination modeling on April 9th. And we will wrap up the series on April 16th with fatigue crack propagation. So once again, you can follow the link at www.ozeninc.com, which is shown in here, so it appears at the very first page. Here you can register for the upcoming webinars. So with this, I would like to thank you for those who has attended this webinar. And once again, we will be uploading a recorded copy of this webinar to Ozen Engineering website. And if you have further questions, please feel free to contact us at this email info@ozeninc.com, or you can call us at 408-732-4665. So have a great day and take care.